What specific problem does the 2-number-2 watermarking method aim to solve, and what gaps in existing research does it address?
The 2-number-2 watermarking method aims to address the problem of reliably detecting whether text generated by language models, LMs, is watermarked, thereby preventing misuse such as academic plagiarism and disinformation campaigns. It specifically targets the limitations of existing watermarking schemes that either compromise the quality of generated text or lack robust statistical guarantees for detection. The method fills gaps in prior research by introducing a watermarking approach that modifies model weights through Gaussian perturbation, ensuring that the generated text remains indistinguishable from unwatermarked text while maintaining high detectability and robustness against common corruptions. Additionally, 2-number-2 provides formal statistical guarantees on its validity and power, which are crucial for practical applications where authorship claims are sensitive. Overall, it offers a practical, efficient solution that integrates seamlessly into existing inference pipelines without impacting generation latency.
How does the proposed 2-number-2 watermarking method work? Please provide a detailed step-by-step illustration of the algorithm, including both the generation and detection components.
The proposed 2-number-2 watermarking method consists of two main components: the generation procedure, denoted as 1-number-1, and the detection procedure, denoted as 3-number-3. 1. Generation, 1-number-1. The watermarking key is generated by sampling from a centered multivariate Gaussian distribution with a specified covariance. This key is then used to perturb the model weights by adding the sampled noise to a single feed-forward layer's parameters. When a prompt is provided, the model generates watermarked text by sampling from the modified distribution, which incorporates the perturbation. 2. Detection, 3-number-3. The detection process involves testing a composite hypothesis that the generated text is independent of the watermarking key against the alternative hypothesis that they are dependent. This is done using a test statistic derived from the log likelihood ratio of the data under both hypotheses. If the computed statistic exceeds a certain threshold, the null hypothesis is rejected, indicating that the text is watermarked. This method is designed to be efficient, maintaining model performance while ensuring that the watermark is detectable under various conditions, including robustness to certain types of text corruption.
Can you provide a simple but illustrative example to showcase the inner workings of the 2-number-2 algorithm? Walk through the key algorithmic steps using this example.
The 2-number-2 algorithm operates through two main procedures: watermark generation and detection. For illustration, consider a scenario where we want to watermark a text generated by a language model, LM, using a specific prompt. First, in the watermark generation step, denoted as 1-number-1, we sample a watermarking key from a centered multivariate Gaussian distribution, which introduces a small perturbation to the model's weights. This perturbation modifies the model's parameters, allowing it to generate watermarked text that retains high quality while being statistically distinct from unwatermarked text. Next, when we want to detect if a piece of text is watermarked, we use the detection procedure, denoted as 3-number-3. Here, we test the hypothesis that the generated text is independent of the watermarking key against the alternative hypothesis that they are dependent. If the test statistic exceeds a certain threshold, we reject the null hypothesis, indicating that the text is likely watermarked. This process ensures that the watermark is detectable while maintaining the integrity and quality of the generated text, demonstrating the effectiveness of the 2-number-2 algorithm in practical applications.
What are the theoretical or practical benefits of using the 2-number-2 method compared to existing watermarking techniques in terms of efficiency, detection power, and impact on model performance?
The 2-number-2 watermarking method offers several theoretical and practical benefits over existing techniques. Firstly, it is designed to be efficient, as it incurs no additional computational cost during inference and integrates seamlessly into existing generation pipelines, maintaining generation latency, page 7. Secondly, 2-number-2 demonstrates significant detection power, as it is empirically validated to be very detectable while also being robust to various types of corruptions, including token-level and semantic changes, page 16. Importantly, it does not significantly degrade model performance, as extensive evaluations show that the quality of generated text remains on par with unwatermarked counterparts, page 13. Additionally, the method provides formal statistical guarantees on validity and power, ensuring reliable detection in practical scenarios, page 10. Overall, 2 stands out for its combination of speed, robustness, and minimal impact on model quality, making it a compelling choice for watermarking language models.
How was the effectiveness of the 2 method validated through empirical testing? Discuss the datasets used, performance metrics, and the experimental design that demonstrates its efficacy.
The effectiveness of the 2 watermarking method was validated through extensive empirical testing, using the real news-like split of the C4 dataset as prompts for generating watermarked text. The experimental design involved evaluating the detectability of the watermark, the impact on model quality, and the robustness of the watermark against various types of corruptions, including token-level attacks and round-trip translation. Performance metrics included the detection power of the watermark at different corruption levels, as well as comparisons of the quality of generated text against unwatermarked counterparts, using frameworks like Eleuther's LM Evaluation Harness and Alpaca Val. The experiments demonstrated that 2 maintained significant detection power, even with substantial token corruption, and did not lead to a statistically significant decline in model quality across various understanding, reasoning, math, and conversational benchmarks. Additionally, the speed of both generation and detection was highlighted, with 2 achieving rapid processing times, further underscoring its practical efficacy.
What limitations or drawbacks have been identified in the 2 watermarking method, particularly regarding its robustness to certain types of corruptions or the need for white box access to model weights?
The 2 watermarking method has several identified limitations. Firstly, it lacks formal guarantees of distortion freeness or indistinguishability, which necessitates further investigation into its effects on text quality before practical deployment. Secondly, while it is generally robust, 2 is somewhat less effective against edit-level corruptions compared to some alternative schemes, although it may outperform certain implementations that prioritize text quality. Additionally, the method requires white box access to model weights for detection, which is a stronger access model than many other approaches that only modify the sampling process. Lastly, 2 typically requires more tokens to reliably detect a watermark than some alternatives, although its detection speed compensates for this drawback.